Greetings, everybody. Today's topic is independent events as we continue our probability unit. Only a couple more sections to go. Independent events and then dependent events is next, and then we will get ready for an assessment. So here, there's some definitions here to start out. I want everybody to read this. To determine the independence of two events, check to see whether the probability of A given B equals the probability of A. Now, why would that help us determine independence? Well, let's back up and define what independence is. Independence means one event does not affect the other, okay? So if the probability of A given B is the same as the probability of A, that means that event B is having no effect on the probability of A, if that statement that I circled is true. So that is why we can check these calculations using two-way tables to gauge whether these probabilities are the same or not. If they are the same, then we say the events are independent. If they are not the same, then the events are dependent. So let's see what this looks like in an example. This, again, as always, this blank notes copy and the key are linked on our agenda. So here, for example 1, the two-way frequency table gives data about 180 randomly selected flights that arrive at an airport. Letter A is the event that a flight is on time, independent of the event that a flight is domestic. So let O be the event that a flight is on time and D be the event that a flight is domestic. Let's determine independence. So let's calculate these two probabilities. First, let's look at the probability of on time given domestic. So that is a row relative probability. So we are specifically focused on this row because we are given that the flight is domestic. So given that the flight is domestic, we're looking at those 120 flights. How many of them were on time? 108 of them were on time out of 120. That reduces to 9/10. Now let's look at the probability that an event was on time. So that is just a marginal probability now. The probability that an event, that a flight was on time is 162 out of 180. So here we'd have 162 over 180. Well, guess what that reduces to? 9/10. This means that our events are independent events because these probabilities are the same. In other words, the fact that the flight was domestic had no bearing on whether or not the flight was on time. The probability of being on time was the same whether or not the flight was domestic. So the events are independent. Is the event that a flight is international independent of the event that a flight arrives late? For this, we'll need to look at the probability that a flight is international, and then we'll look at the probability that a flight is international given that it's late. So the probability that a flight was international, or is international, would be 60 out of 180. So that's a third. And then the probability that a flight is international given it's late, so now we're just looking at these late flights right here. 6 of them were international. So that's 6 out of 18, which reduces to 1/3. So again, these probabilities are equal, therefore these events are independent. The fact that the flight was late, or the fact that the flight was international, the probability of that happening is the same regardless of whether or not the flight was late or not. So in other words, being late was not affected by the fact that the flight was international. So both of these events, A and B, are independent events. For this problem here in B, we could have looked at the probability of late and the probability of late given international, and we should have gotten the same probabilities there as well. That would also show that the events are independent. Let's look at a proof here. Events A and B are independent if and only if the probability of A overlap B, or probability of A and B, equals P of A times P of B. So for this proof, we're going to use a statement that we used for conditional probability. We're going to start off by saying probability of A given B is the same as probability of A overlap B over P of B. And that was definition of conditional probability. All right, well, if I am assuming that events A and B are independent, so I'm going one direction, here's my P and here's my Q over here, I'm going to assume they're independent. Now, I could prove this both directions. I'm just going to prove it the direction we're doing right now, though. If I assume A and B are independent, then the probability of A given B is going to be the same as the probability of just A. Because if they're independent, B won't be affecting A at all. So I'm just going to replace that, and I'm going to leave everything else the same. And for my reason, A and B are independent. Through multiplication property of equality, then, I can get P of A times P of B equals probability of A overlap B. And that's multiplication POE, property of equality. So there's my formula right there. So if two events are independent, then the probability of A and B is P of A times P of B. That's going to be helpful here. We're going to apply that here in example 2. You spin a spinner with 4 red sections, 3 blue sections, 2 green sections, 1 yellow section. If all the sections are equal size, what's the probability you spin a green first and then a blue second? So the probability of green and blue is going to be the probability of green times the probability of blue, because these two spins are independent of one another, right? The first spin doesn't affect the second spin. They're completely independent events. So to find the probability of a green and then a blue, multiply these together. The probability of green would be 2/10. Probability of blue would be 3/10. And that reduces to 3/50, which is 6%. Letter B, 2 at-home security systems work independently of each other. One has a success rate of 95%, the other 97%. What's the probability of at least one of the alarms does not work? So to do that, the probability that at least one of the alarms does not work. So let's let NW be event that alarm does not work. Okay, so let's find the probability of not working for the first one and then not working for the second one. That probability would be 0.05, which is 100% minus 95%, or 1 minus 0.95, which is 0.05, times the probability of the second one not working, which is 0.03, and that equals 0.0015, which is 0.15%. So that's the probability of both of them not working. Now let's consider, is the probability that we just found really what we are seeking here? We want the probability that at least one of the alarms does not work. Well, what is the complement of what I just said? The probability of at least one of the alarms not working, the complement of that would be them both working, right? So what if we just found the probability of them both working? I'm going to put a little line right here. What if we just found the probability of the first one working and the second one working? That would be 0.95 times 0.97, which equals 0.9215, 92.15%. That's the probability of them both working. So then that means that the probability of 1 or 2 not working would be 1 minus that. So the probability of at least one not working would be 1 minus 0.9215, which is 0.0785. 7.85% would be the probability of at least one of them not working. The probability of both working was 92.15, so the probability of essentially anything else happening is 7.85. So that actually is the answer to this question. This would be the probability of both of them not working, very minuscule, 0.15%. Let's look at the final piece of the lesson today. Here's a definition that we need to be aware of. First of all, biconditional statements, that means statements that are true both directions. So if P then Q, if Q then P, it's true both directions. If and only if is the way you say or state that a statement is biconditional. And here's an example. There's a biconditional statement. You just switch the P and the Q. Contrapositive, what's the contrapositive of the statement 1? Contrapositive is when you flip the order and negate. So if you flip the order and negate, so it would be if P probability of A intersection B does not equal P of A times P of B, then A and B are not independent. Or in other words, they would be dependent. So that's how we're going to determine independence and dependence here as we check in, or at least that's one way we can determine independence and dependence. And we could use that strategy in example 3 if we want. I'm going to use the strategy that we learned earlier as well here. So here's some data. There's 120 randomly selected patients, same doctor, and you're looking to see if exercise and vitamins are related or not. So I want to determine whether a patient who takes vitamins and a patient who exercises regularly are independent events. So to do that, I'm going to take a look at the probability that somebody takes vitamins, and I'm going to take a look at the probability somebody takes vitamins given they exercise. And if these two events are independent, then those two probabilities will equal each other. If they don't equal each other, the probabilities, then the events are not independent. So let's look at the probability that somebody takes vitamins. That would be 60 out of 120. So that is 1/2. Probability that somebody takes vitamins given they exercise. So now I'm just looking at the exercise row, and that is 48 out of 76, which is 24 over 33. And because these two are not equal, that means the events are dependent events. And if we use the formula that we just talked about on the top of this last slide here, we could do that. We could look at the probability that somebody exercises and takes vitamins, which is 48 people out of 120, and see how that compares to the probability that somebody takes vitamins, 60 over 120, times the probability that they exercise, 76 over 120. If you calculate that, these are not equal. This times this does not equal 48 over 120, so that is another way of showing that these two events are not independent, or in other words, they are dependent. That is all for our lesson today. Feel free to rewatch this video as much as you need to. Pause it along the way. Again, the notes and the key for this are available on the agenda. Schedule a conference if you need any help. There's a practice that goes along with this on Schoology for you to check out. Do expect some kind of quiz or test over probability around the middle of next week is the plan. Again, the middle of next week. So between now and then, just keep practicing, keep doing the practices that I provide to you, and we'll go from there. More information coming, so stay tuned on that. Thanks for watching.